for this Mossbauer spectroscopy, in which we have to see the actual interaction that we call as the hyperfine interaction. So where we see there are different key factors, but here we have to see why interaction would happen. There is having electric monopole interaction, electric quadrupole interaction, as well as there is having magnetic dipole interaction. So how it is? So there are different types of interaction. Majorly electrical monopole interaction, electrical quadrupole interaction, and this one is having magnetic dipole interaction. So there is having r square radius, which having there is a radius would be different with respect to the source and absorbers. In this case, electrical quadrupole moment which is not equal to 0 and spin is greater than 1/2. In case of dipole interaction, there is a magnetic dipole moment would not be 0 and it is the I value is greater than 0. Here is a magnetic applied field is not equal to 0. Here electric field gradient would not be 0 and this electronic condition would not be same. Then and then they have to show such type of interaction. So in case of electric monopole interaction leads to isomer shift, while electric quadrupole interaction leads to splitting at a two-fold degenerate energy, and that we call as a quadrupole splitting. While in case of magnetic field, it gives to be magnetic dipole splitting. So that way these are the some consequences of this Mossbauer spectroscopy where we have to see it. Then actually how isomer shift which we observe. So isomer shift is observed due to the Coulombic interaction between the proton of nucleus and electron, basically S electron. The question is why this slight shift of MB energy level would happen even though they have not split at nuclear energy level. So that split MB spectrum shift was observed because source is different from the absorber. This is the one case. Another case is a nuclear radius in its ground and excited state would be different, nuclear radius. Third one, electron density of all S electrons are also having different. So this image here we have to see the source and absorber. Nuclear radius is also source and absorber are not equal. Electron density is also not equal, and which leads to electrostatic interaction between charge distribution of nucleus and those of electron which having finite probability around the nucleus. So whatever the S electron present around the nucleus having major influence on the electron present on P and D, which we call as a screening effect, which leads to isomer shift. Then factor affecting for the isomer shift, that's S electron density and number of D electron. If it is having more S electron density, more positive delta value. More D electron density, more positive delta value. Here are some example in which 10 plus 4, which having 5H0, 5P0, which having the very less electron density, delta value decreased by 2 mm per second. While SN2 plus, it is increase more S electron density because 2 electron in S orbital. Similarly for Fe plus 2 having increase more electron density. So it is increased by 1 mm per second, while Fe plus 3 there is having less electron, 1 electron is less, and therefore it is decreased by the 1 mm per second. So that way these are the number of electron present in the orbitals leads to shifting of a delta value, that is the isomer shift. So what are the basic factors are mainly responsible for the isomer shift? Majorly high spin and low spin complexes. High spin complex or low spin complexes leads to number of electron present in its d orbital. So Fe plus 2 with having high spin is a higher delta value. High spin means maximum number of unpaired electron, while Fe plus 2 plus 3 is comparatively less, and then Fe plus 2 low spin, and then Fe plus 3 low spin. So there is a decreasing value of a delta value. So whenever there is having more S electron density, then more delta value, and more D electron density, more delta value. So these are the factors mainly responsible for the isomer shift. Another factor is having electronegativity. In case of electronegativity of atom decreases, electron density electronegativity atom decreases electron density and reduces delta value. If see the example SN4 plus compound and SN2 plus compound, in which fluorine, chlorine, bromine, iodine, in which we have to see there is a decrease in electron density from fluorine, chlorine, bromine, iodine, and it reduces its value. For that way we get it at example how there is a shift with respect to electron density. Then there is also bonding between the metal complexes. So delta value is less if it is having strong ligand, and it is higher for the weak ligand. So this is the image where ligands of nitrosyl plus cobalt, triphenyl phosphine, NO2, NH3 and water, where there is an increase in delta value would be takes place. So this ligand, nature of ligands is playing major role. There is a shift of delta value. Okay, so it should be moved towards the higher or lower depending whatever its nature. Then we have to see the how many number of signals we get it. In case of MB signals, equivalent show it used to be only one peak, while non-equivalent show the two peak. So you have to see here example. So these are the two examples. There is a 3 carbonyl, 3 carbonyl, 3 carbonyl. So this is the equivalence. This one equivalent and this one equivalent, and this is a cross. I put it in cross way, and this is non-equivalent. So non-equivalent used to be 2 peak because 2 different environment, while it is equivalent it used to be 1 peak. Then question arises, what it mean by quadrupole? Quadru means 4 and pole. When there is a having symmetrical distribution of this electric quadrupole or magnetic quadrupole. So this is the quadrupole with having symmetrical distribution, and this is the when I is equal to 0 there is a symmetrical. When I is equal to 1/2, so it should be look like to be this one elliptical. This again Q is greater than 0, again become it is elliptical, or it is Q is less than 0, it is like to be this horizontal elliptical. So that way we have to see when I is equal to spin is greater than or equal to 1. So that way electrical quadrupole and magnetic quadrupole can create electrical field gradient, and that electric field gradient mainly depend on what is the environment present around that nucleus. So how that can play major role. So interaction between nuclear quadrupole moment. Nucleus is having its own quadrupole moment, which is surrounded by electrical field gradient. So here this image tells us how. So this is the nucleus having its own nuclear quadrupole moment, while surrounding field, these are the surrounding field. So electrical field gradient. So there is an interaction between nuclear field gradient, nuclear quadrupole moment and electrical field gradient. So that interaction leads to there is a asymmetrical interaction and split at nuclear energy level. So in this case, when isotopes with having I 3/2 is an excited state for the iron 57, tin 190, and which show the transition from 3/2 to 1/2 and split into 2 different energy level, and which used to be plus or minus 1/2 and plus or minus 3/2, and it appear 2 specific peak of the spectrum that we call as a doublet, or that we call as a quadrupole splitting, and which can measure with respect to its electrical field gradient. So this is the image where we get it how it is work. So number of signal and splitting of signal. So this is the 3/2 and 1/2. So whenever there is an interaction, this is the isomer shift. Shift would be takes place that we call as isomer shift, and this is the electrical field gradient and nuclear quadrupole moment interaction leads to these two absorption. This chemical shift and quadrupole splitting, which we have to observe in this case. So similarly for the different images where FeCN6, it is strong field iron complexes with having the T2G6 electrons. So Fe plus 2 there is having electrical field gradient is 0, while T2G5 when electrical field gradient is not equal to 0. So that way we get the absorption of light. This spectrum, it used to be 2 peak or 1 peak. So that way symmetrical and unsymmetrical distribution of electron leads to such type of MB spectrum. Then question arises, that magnetic dipole moment. So magnetic dipole interaction between the nucleus and surrounding magnetic field. So how it is work? There is a rule for magnetic dipole, means there is a excited state and ground state. So there is a transition would be takes place. So for that purpose, what we are doing? So nucleus with having spin I is not equal to 0, split into 2I plus 1 sub energy level, and therefore whenever they have to split into this sub energy level, it used to be 4 non-degenerate substates, that is plus 3 by 2 plus 1 half minus 1 half minus 3 by 2, and that leads to these peaks. So that way it used to be this non-degenerate energy level. So this energy level, they have to split it and they have to show such type of spectrum. In this case we get only 6 peaks, and which is hyperfine splitting interaction, and that would be happen due to the magnetic dipole interaction. So this is the last picture which gives an idea about how it is work. So these are the nuclear energy level. So hyperfine interaction, source and absorbers. But when I is equal to 3 by 2, I is equal to 1 half, so there is an exact resonance, then hyperfine interaction. When there is an isomer shift occur, they have to shift slightly, so that shift. So this one, hyperfine interaction, this is from 0, where there is a complete MB spectrum, that is with respect to natural bit. This is a shift from here, so that we call as a isomer shift. Here quadruple splitting, they have to split this energy level split due to the electrical field gradient of the electron, surrounding electron with respect to nuclear quadrupole moment, and which leads to these 2 peaks that we call as the electrical field gradient. And then this is the magnetic splitting, where when there is a applied magnetic field, they have to split into 2 different energy level, leads to such type of different peaks. So this picture gives an overall idea about the why we get such type of peak from here to here. So hyperfine interaction, isomer shift, quadruple splitting, and magnetic splitting. So these are the applications of this MB spectroscopy. That is it is used for iron mineralogy and speciation. It is also used in different non-destructive method to identify whatever the portable field. Then it is also used in various microscopic sample. So I hope so. Thank you to all of you. That this would be very little bit faster, but I feel that it would better for us to understand how this spectroscopic tool work for the different application. Thank you so much.